if you take Newtonian gravity and equivalence principle very seriously, according to equivalence principle, something that's falling locally will say that it is inertial. Therefore, it would say that it has a straight world line, something like alpha plus beta t. Right, this straight line. It's falling freely, and it says it has this world line. You look at it and you claim that it has a world line. What that tells us that there's some kind of transformation between the two frames, which turns t into t. In other words, time is kind of stretched. If you look at it in terms of work, time is stretched. It's a function of where you are. If you have this, let's say, spherical source, and you're here or you're here, the time rate here compared to here will show up. There'll be a variation in the time amount of time passage between here and here. Therefore, you get the redshift and so on and so forth. Here, you have, at each point in space, you have a different, let's say, we'll draw the time axis. You have to stretch this one based on where it is according to r. The closer it is to the source, the more the stretch. The closer it is, the further from the source, the less the stretching. What's going to happen as a result of the stretching is a straight line turns into a curved line, or a curved line can turn into a straight line. If you stretch this, then the scale changes, and what would be curved in one thing becomes straight in the other. If you just say, well, t is stretched, it becomes a function of t. Obviously, the way that I measure time in a gravitational source is different than the way that I should measure time in empty space. Infalling, let's say, to spherical symmetry, you know Newtonian gravity, and you found that for infalling, obviously r double dot is equal to gm over r squared. This is simply a differential equation. What's the solution? Does anybody know offhand? What's the solution for r of t? What is the solution for r double dot over r squared? It's simply proportional to t to the 2/3. Okay? All right? Does anybody know if you solve the equation r double dot equals gm over r squared, and you want to find the world line equation in flat spacetime, r of t? What is r of t? What's the equation for r of t? Just in ordinary gravity, gm over r squared. What is it? Okay, what's the formula? Has anybody ever seen it? Okay, you have it worked out over there. It's t to the 2/3. R is t to the 2/3. That's simple calculus. If you take the second derivative of t to the 2/3, you end up with 1 over r squared. Okay? You probably all solved in general relativity, and this is also for black hole collapse. It's also for cosmology. Same thing. And this is a very important equation. In general relativity, for example, collapse to a black hole is governed by that. The Big Bang expansion, if you want to find the age of the Big Bang, this is what turns up. So this t to the 2/3 comes up all over the place. All right, so you have this page. You can just see it's just ordinary calculus just to find the solution of r double dot equals 1 over r squared. Simple differential equation. All right, if you substitute t to the power n, which I give as an example, you find that n is equal to 2/3. All right? If you take Newtonian gravity and equivalence principle very seriously, something that's falling locally will say that it is inertial. Therefore, it would say that it has a straight world line, something like alpha plus beta t. You look at it and you claim that it has a world line t to 2/3. What that tells us that there's some kind of transformation between the two frames, which turns t into t to the 2/3.
So now, mathematically, just in a simple way, if you have an inertial particle or an inertial frame, and it's in a warped space-time, it's actually a free-fall frame, and you'll take some kind of coordinates and you'll say that this is equal to 0. Okay, my acceleration is 0, and these are good valid coordinates. Taking the equivalence principle along some given geodesic and saying you have this free fall particle, we know that that's the inertial particle, that's the geodesic, and therefore I'm going to write this straight line equation, even though ordinarily, naively, Newtonially, I would never have written this equation. I would have written that this is equal to minus gm over r squared. The ordinary Newtonian, you would say you have a particle, it's falling, it's accelerating. Yeah. You have the second derivative of x with respect to t is minus gm over r squared.
Yes.
Right? But because of the equivalence principle, I'm going to say that it's 0. This is a geodesic equation. If you take seriously the fact, and you agree that one can see this free-falling particle's world line as a geodesic,
yes,
right, then, it's a straight line. So I write the straight line equation. This is what Misner Thorne Wheeler does. He doesn't talk about warping time. He talks about just how you define time.
Sure.
Right.
Sure.
But I'm just using that calculation. Now I'm going to transform to a different frame in which I have a poor definition of time. This is the warped time, which is the true perspective, and I'm going into now comparing it to a frame in which I'm using the time that we naively use in Newtonian physics, which is not warped. We're not taking into account the warp. So where this time is a function of this time, right? It's some function. In other words, basically, it's a stretch. It's a one-dimensional parameter change. Okay. So it's this plus this equals 0. Which means that this equals to this, and there are minus signs and so on. So basically, I now have a new phenomena using the x coordinate and my bad time, so to speak, right? You'll see that this is equal to minus this over this. So you have an acceleration given by this. All right? So that's the bottom line. The conclusion is that you will notice if you're using an axis system, using this bad choice of time,
yeah,
right, you're going to claim that you're going to see this.
Yeah.
So you see an acceleration, and this is the amount. Again, if you're just having a one-dimensional line, you can reparametrize O's. But if you have this space axis here, so that you have a relative scale between them, that's the thing that allows you to actually define this in a way which can't be reparametrized. If there really is this time warping,
yes,
and what I'm saying is that really it's the free fall frame which has this equation true,
yeah,
all right? If I'm going to be using a non-free fall frame, like this supposedly, allegedly Newtonian inertial frame of a stationary person, right? You're going to end up, and if you're saying that the difference between them is a transformation of the time, then this is how the acceleration would arise as a result of that, in a schematic way. Of course, one has to define carefully a space-time and what does it mean to warp space-time and so on, but this is the phenomena, this is how the phenomena would look in a kind of like a heuristic sense. This is really the geodesic equation, and that if you stick in that this is just t, you get the same thing, you get exactly this.
right.
This is from Weinberg. He does a very nice calculation here.
Right.
Does this is the second derivative equal to 0.
Right.
It's very similar. He's doing it, of course, for a covariant system where you're transforming space and time.
Right.
I'm doing it specifically for time only.
Okay.
right?
Sure.
But basically, when you do this, you end up getting the geodesic equation,
Of course. Yeah.
right? And if you do it, here I just wrote the psi going to x of Misner Thorne Wheeler.
That is Minkowski sphere.
Right.
Space can transform
Right.
by some coordinate system.
Right. So if you defines what the Christoffel symbols are based on this transformation,
Okay.
so you can see that it's an acceleration basically.
Okay.
And he then shows you if you're transforming the Euclidean, well, the Minkowski metric,
yeah.
you end up with some transformation that he defines as the metric
Of course.
coefficients, right?